Welcome to the Rich Report, a podcast with news and information on high performance computing. Today, my guest is Jeff Squires. He is from Cisco, but he's also one of the key people working behind the scenes on MPI standards going forward. So, Jeff, how are you doing today?
Good. How are you doing, Rich?
Great. I'm in Portland. It's actually not even raining at the moment. So
Wow.
yeah,
It's a good day.
it's a good day indeed. But Jeff, I saw you had some slides that came up, and I thought, geez, let's get Jeff on here. This looks interesting. Making MPI more awesome. How did
Absolutely.
how did this get started?
Well, yeah, so this is actually a group of us, and I want to stress that, this is not just me. There's a whole bunch of us, and you can see all the names on the first slide here of all of us who are involved in this, who just kind of, I gave this crazy talk at the Euro MPI conference last year in Bordeaux about some kind of just ideas that have been rattling around in my head for a while. I'm like, why doesn't MPI do this? And why doesn't MPI do that? And over a couple glasses of wine in Bordeaux, and then later a couple of glasses of beer in the next MPI forum meeting in California, and follow on to that, a bunch of us just started talking, saying, well, yeah, why doesn't MPI do these things? Why can't we do some modern things and just make it kind of more awesome and not just have these little evolutionary changes, but maybe a couple of revolutionary changes
Hmm.
that are, not just cool, but genuinely useful to the HPC community. So, that's where all this came from. Over the last several months, we've just been kind of meeting in a sort of regular fashion and saying, let's take some of these ideas and see if we can actually make them real.
Okay.
And what just happened was last week, we finally took all these ideas and presented them to the forum itself. And I do want to stress, this is all a proposal. It could be totally different or not happen at all. This is just kind of a window into the process of how the MPI forum itself creates the standard. So, we'll see where this goes, but it
Hmm.
looks really promising.
Okay. So this is a first step, and would this possibly come into MPI 5 or something, or what do you think?
In a perfect world, it would come in MPI 4, which is still at least a year or two away.
Yeah. Yeah.
But there's a lot to this, and on my blog, I put the slides that we presented, and that's like a super dense and a lot of connotations and implications in those slides and stuff
Hmm.
like that. So today, I tried to make a little summary of what we're talking about, some of the top level ideas to give your readers and listeners a taste of what we're talking about here.
Oh, okay. Okay. Well, I've got the slides up. Let's go through that.
Okay. All right. So again, just stress the two things. There's a whole bunch of people involved here. You can read all the names and the organizations who are involved. And this is a proposal. It could totally change. It could totally flop, or it could go in exactly as we see. We can't really predict the future. But let's dive in a little bit to some of these first ideas here. All right, oops, there we go. So a couple things that we were talking about, and some of the things I was asking about at that talk way back in Bordeaux at Euro MPI. MPI version 3.1, which is the current version, has a couple of well-known limitations to it, right? And they're centered around the idea of having multiple entities in a single process, like multiple libraries. Like, let's say you got your LAPACK and your PETSC or whatever scientific libraries you've got to help your application out. They can't really initialize MPI without either some a priori knowledge or coordination between them and stuff like that, which kind of is annoying. You really want to just have a library be able to just start using MPI and doing what it wants to do. Another thing that's kind of a historical holdover is that you can't initialize MPI more than once, which further creates problems for that first bullet up there if you have multiple entities who want to use MPI. Also, similar but different, you can't reinitialize MPI after it's been shut down. So once MPI is shut down, you're done. It's time to just quit the process, basically. Save your results, you're done. And you also can't set the error behavior, right? So if an error occurs, you might not want to just abort the program. You might want to do something a little more interesting. Save your results, do a checkpoint, who knows what you want to do. But you can't right now the way that MPI 3.1 is defined. So really what we want in summary is just, if you have all these libraries in an MPI process, you want to let any library, perhaps even any thread, use MPI anytime that it wants. However, you still do want to preserve the ability to totally clean up MPI when and if you want to. So it's nice from a tools perspective to be able to monitor and make sure, like, oh yes, I have shut down all of my MPI usage properly. So that's an important property to maintain. Well, okay, that's all fine and great. How do we get these things? Well, here's this concept, right? And that's right in the title, the session stuff. We created this idea called a session. And a session is actually something very simple. It's just a local handle to the MPI library. And again, this is not even groundbreaking. Lots of APIs out there have this kind of session that when you open up the library per se, you get a handle back. And that is your conduit to talk with the library. And our intent here is that this is a very lightweight kind of object, right? It uses very few resources. It could actually be tied to hardware resources, like some queues down on the network interface or something if you want to. And I'll get a little bit more into that later. But it can also cache some local state. And then key to this is that you can have multiple sessions in an MPI process. So if we have some new APIs like session init and session finalize, you can get this handle back. Let me show you what it would look like. All right, so let's say I've got an MPI process like this, and I've got two libraries in there, Ocean and Atmosphere. And if they both call session init, they're both going to get a handle to the MPI library that's unique and private to them, that's their conduit to the MPI library. And on those session handles, they can cache unique things. They can have different error behavior, different info keys. They can have local state and things on there. It gives them kind of this just private local conduit to the MPI library. Well, that's all fine and good. What exactly does that give me? Well, okay, now we're gonna go into totally uncharted territory here. Is that something that quite intentionally, actually, for the last 20 years, the MPI definition has rigidly taken a stance of not talking about the underlying runtime system at all. Right, and this, like I said, has been very intentional. But the standard itself barely acknowledges the underlying runtime system, mostly in the form of suggestions to implementers or advice to users and things like that. But we think it's really kind of time to change that, particularly when we're trying to gear up for exascale and more exotic types of HPC resources. We think MPI might need to be in a bit more of a collaboration with the runtime rather than try to be the entire master of the castle itself. So here's the general scheme that we're talking about. That first you get this session, right? That session init call, right? And then here's the mind-blowing part. You can query the underlying runtime system and find out who your peers are. You can get sets of processes. From that set of processes, you can get an MPI group. And an MPI group is something that's been around for 20 years. So we're actually taking advantage of some of the richness of the MPI API that's been around for a long time. And part of the advantage of that is that there is a huge, rich set of API functions to slice and dice and reorder and reshape a group however you want it. And then once you get that group the way you want it, then you can actually make a nice heavyweight communicator and do whatever it is you want to do with your MPI application. But all the way up to that, the session, the query, the group, that's all super lightweight and local stuff that you can do algorithmically and take very few resources to represent. And then you get into the actual communicator when you're doing the sends and receives and puts and gets and all these kinds of things in the rest of your MPI application. So here, this is the key process here, right? Or the key concept that we want the runtime to expose these sets of processes. And we're going to mandate that two sets are exposed. And we're using kind of the URI syntax because, again, let's be like the rest of the world. Why make HPC a one-off? There's a lot of things that we can share with the rest of the world to make it easier for people to get into HPC. So let's use a familiar construct like a URI. So MPI://world. Right? Let's use a nice string to represent the COM world, the communicator that represents the whole world. So here we have these sets like this. Let's say we launched 4 MPI processes, and here's what that set of processes would span. Right? But I might also have other names like, oh, well, give me all the x86 64 processes and stuff, or maybe all the processes that are in my job, right? So one process can be in multiple sets depending on how you want to discover it. And These are all kind of implementation dependent kinds of things. Some other interesting ones, there might even be some sets that give you a little bit of information about the topology of the HPC resource itself, maybe some network or hardware topology kinds of resources that we really know, like, hey, these two processors over here in rack 17, these guys over here in rack 23. Maybe you want to do something with that information inside your application to take advantage of the locality. All these things are possible. Well, this all sounds great, but how exactly does this relate to MPI NIT? How does this solve some of the problems that I talked about in the beginning? And by the way, what about CommWorld and CommSelf? We didn't talk about those at all. What session do they belong to? Well, okay, what if we have another mind-blowing concept here that we no longer require the application to call init and finalize? Right? Well, that's kind of craziness. What exactly does that mean? Well, remember we said at the beginning that kind of our goal here is that MPI can just start using the functions whenever you want to. Initialization actually kind of becomes a hidden detail on the back. What do you care when MPI initializes and finalizes? You just want to use MPI functionality, right? Finalization will occur when finalization occurs. Initialization will happen whenever it needs to happen, right? Now, you can actually get down to a nice clean state if you want to. If you destroy all of your MPI handles, then the MPI will actually finalize. You can be tool clean for tools like Valgrind and other memory checking debuggers, and that's a very useful property like I mentioned in the beginning. But other than that, you really don't care. You want to just start using MPI. Now, here's what it would look like, right? Let's say at the very beginning of my program, I can just call an MPI function like MPI type contiguous. We won't even go into what that does, but suffice it to say, it does some MPI stuff. There was no MPI init before it, no session init and things like that. The creation of the first MPI user-defined object is what initializes MPI under the covers. And then when we're done, let's say we free it, well, that's going to finalize MPI perhaps under the covers, and then you can be done. Right? That's as simple as it is. And it's a little bit of a liberating concept. Just use the API whenever you want to. Who cares about initialization and finalization? And by the way, we can reinitialize MPI 2, which is another shortcoming of MPI 3.1 today. So if I just call another MPI function, boom, underneath the covers, if the MPI needs to do something, well, it'll do that. That's awesome, right? Now, here's the key insight here. Because, getting rid of it and finalize, that's nice, but why do I care? Why is that important? Well, let's take a step back here. Let's take a key insight here is if you split the MPI API into two sets of things, you can abstractly think of the stuff on the right is where performance is really, really important when you're doing your MPI sends and your scatters and your gathers and your broadcasts and things like that. Performance really, really matters, right? A lot of people get squirrely when we say, oh, we need to add additional checks in the code path there, like make sure MPI is initialized, and if not, go initialize it. Nobody wants to add any instructions in the code paths on the stuff on the right. But on the stuff on the left, performance doesn't really matter as much. Of course, it's still a well-performing library, but all the things that create and query, all these functions, communicators, files, info, all that whole list of stuff, it really isn't that matter if we add a couple of if statements in that code path. Nobody's really going to object to that. All right, now, why am I bothering? What's the point here, splitting this into two sets? Well, here's the insight. The stuff on the right can't be used unless MPI is initialized, right? So the stuff on the left, we can add stuff in there to transparently initialize and finalize MPI. And then further, the stuff on the right can't be used unless you have something from the left. And this is not new. This is just the way the API was actually designed. Good design over the last 20 years of the MPI API says, okay, we have to create all these handles, and then we can actually do performant things with them. Right? So the API is actually already well designed in this kind of bifocal way that I can do something a little bit slow, and then I have a nice optimized common case for my point-to-point, my collectives, my I/O, my RMA, all these kinds of things, right? So the point here being is that we don't have to add anything to the stuff on the right, because by definition of the API, it's already handled for us. You can't call the high performance absolutely matters functions on the right until you have already called something on the left, where it doesn't matter if we add a little stuff to initialize MPI and things like that. Well, now wait a minute. That's not entirely true. There's at least one corner case that everybody asks about. Well, what about CommWorld? CommWorld is this predefined communicator that MPI says is available for use. So right away, your first statement in main, you could just say, hey, MPI send on CommWorld. Well, we're saying no. This is actually, we're going to disallow this, because this would be calling a performance matters kind of function before you've called any of the performance doesn't matter kind of functions, right? So MPI has not initialized yet. Well, that's still kind of crummy, right? We can make a special exception for this, but it's kind of crummy. So what about MPI init? What if people actually still do call MPI init? Well, that's fine then, right? They can call MPI init, and that sets everything up, and then they can call MPI send and still get the super high performance without additional if statements and all these kinds of things. So how can we incorporate that into our new ideas here into the sessions-based world? Well, what if we redefine what MPI init is? What if that is just the constructor for CommWorld? It might have a side effect of initializing MPI, or it might not if you've already done some MPI before it. But really, all it does is say, oh, after init, you can call and use CommWorld-based things for sends and receives and all the other things that you do with it. And by the way, that is exactly how all MPI 3.1 programs work today. So this actually gives us the backwards and forwards compatibility between an MPI 3.1 world and an MPI 4.0 kind of world, or wherever and if ever this stuff enters the MPI standard, right? So that in itself is also kind of a mind-bending thing. Like, wow, MPI init and MPI finalize are only necessary if I'm going to use CommWorld or CommSelf. They're just a constructor and destructor, and that actually has some very liberating scenarios associated with it. So think of it this way, that init and finalize, they just create an implicit session behind the scenes, and you can't extract it. It's a hidden one, but it creates that session and it constructs and destructs CommWorld and CommSelf. And of course, you can use init and finalize in the same MPI process as other sessions. It's meant to be a backwards compatibility thing and a supporting legacy types of applications kind of thing. That, let's say I have a library that is now using MPI sessions, well, I can still use it in my old legacy MPI application who still calls init and finalize. They will coexist just fine. So here's kind of an abbreviated summary of what we talked about. And there's a lot more detail and a bunch more ideas in the full slide deck that we presented to the forum last week. And there's going to be ongoing discussions. So probably the ideas in the slide deck are going to change over time. But here's this abbreviated summary of just what we've talked about today, is that we're introducing kind of this new concept of an MPI session. You can think of it as a unit of isolation, right? When I've got that process with different entities inside, like an ocean library and an atmosphere library, they are now functionally separate from each other. They don't have to know anything about each other, but they can still use MPI, right? So a session gives them that protection, that sandbox, that isolation from each other, but still have the ability to use the high-performance computing library on the back end. And then we've also defined some interactions with the runtime, right? We said it's probably going to be more realistic to be a collaboration with the underlying runtime as we move forward into complex HPC scenarios and moving into exascale and all these kinds of things. We want to be able to query what's happening underneath, what is some topology information, where are the process sets, make communicators and slice and dice my resources with some application logic. There's some really interesting and fascinating possibilities here. We'll have to see how this shakes out in terms of the standard itself. And then finally, no longer require init and finalize. And in one way, that's just a convenience. But in another way, it's actually absolutely critical to this whole idea of isolation of a session, right? Because MPI init and finalize are global actions. But now we really want to have isolated actions so that it can have these ocean atmosphere sandboxes. So therefore, that was why that's what drove the whole idea of let's make it not mandatory and not global, make it actually tie into this whole session concept, right? And the key insight of what enables that to happen was the good design of the MPI API over the last 20 years that's just had this great consequence of the stuff on the right-hand side of the picture that I showed before really requires you to call the stuff on the left-hand side of the picture before you can do anything. Now, like I said, this is just kind of a summary, a taste of what we talked about. When we presented this at the forum, I think the presentation went for 2.5 hours. This has been about 15 minutes or so. A lot more ideas, and the details are in the full slide deck. And here's the URL of my blog and the name of the entry if you're coming to look at this at some time in the future and you want to go back and look at it there. I'd encourage people who are interested to join we just created an MPI sessions working group in the forum. So a lot of discussions about this stuff are going to go forward, and this is where we're going to see, do these ideas make sense? Is it going to make it into MPI 4? Is it going to make it into MPI 5? Is it going to be changed dramatically? Who knows? We'll see. At this point, these are really interesting ideas, and we had fascinating discussions about them. Now we're going to try and turn it into something real to what the entire world can use.
Wow. Well, geez, Jeff, that sounds really interesting and kind of a powerful. In terms of resiliency, I'm just thinking as we build these larger systems towards exascale, would seem to me to be a great way to keep that machine up and running when some element breaks, right?
Absolutely. So I have to say that the fault tolerance and the resilience scenarios were very forefront in our mind over the last 6 months as we've been talking about this. So some of the names on that first slide are actually involved in the MPI Forum Fault Tolerance Working Group, and they're very excited to see, all right, how can we apply these session concepts to fault tolerance and resilience and migration and all these kinds of things that would be really, really desirable in an MPI and HPC kind of world.
Yeah. Well, Jeff, is there a problem with these? You got all these sessions running around. Problem with them possibly stepping on each other, or is there some kind of lockout? I guess I missed the.
Well, the idea is that they're actually isolated from each other, and they could be isolated just up at the software layer, so that all right, well, ocean and atmosphere in the software just don't know anything about each other, but the MPI library kind of joins them together. So, and sends and receives, the MPI just has to keep them separate. But you could even extend it down to the hardware layer, that if you have 2 sessions in a single process, well, they could actually map to different hardware queues on the NIC. Right, so the ocean library would have its own send and receive queues, and the atmosphere would have its own send and receive queues. So this whole idea of sandboxing the things and keeping them separate from each other is actually a pretty powerful idea that, man, I really hope we can make it work and convince the rest of the forum that this is good stuff.
Yeah. Well, this is probably an unrelated question, but about OpenMP, right? I mean, it seems like MPI and OpenMP were kind of merging or headed that direction. Would this help or hurt, or would it be unrelated?
Well, I think what you were asking was about the MPI forum and OpenMP, right?
Yes.
So yes and no. They are kind of the same and kind of different. I would kind of describe them as like 45 degrees off from each other, right? So OpenMP, at least today, is single machine, right? Where OpenMP or MPI is more about, it doesn't matter how many machines you have. It could be 1, it could be 1 million, right? And so their targets are a little different. But I will say that there's actually quite a few people on the MPI forum who are also on the OpenMP governing body. I forget their name offhand. But so there are people who actually are trying very hard to make these two things play together. I don't think we'll ever merge into one thing,
right?
But I think you could expect over time that we will play better together within the same application.
Well, great. Well, Jeff, I think this is exciting, and I really want to thank you for coming on the show today and telling us more about MPI sessions.
Hey, I appreciate the opportunity. Thanks, Rich.
All right, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.